How long was the list?
49.
And how many are fixed?
1, 2, 3, 4, 5, 6, 7.
Leaving 42.
Which is divisible by 3.
I was just thinking that it's also divisible by 6.
Oh, that's interesting. Yes. Right, there's as I mentioned, the automorphism group of before. Yeah, but what about this? There's actually this even bigger automorphism group. That I don't see. Anyway, okay, so all right, so let's see if we can understand this representation A a little bit. So what's its lowest k-type? Well, so first of all, the fact that it didn't complain means that it has a unique lowest k-type. And what this means is that this is a tautology. So the lowest k, so remember A is this parameter. Its lowest k-type is you set nu is equal to 0, and if that's final, then you're done. And that's this. So in some sense, it's a tautology. But how do we figure out about it? Well, one thing we can do is we can check its dimension. One-dimensional. Let's see. So how do we really tell? So we can do the highest weight of lowest k-type of A. So A is spherical. Okay. Now, I'd like to look at more of the k-types. So that there's a nice command, I think Anna Greth mentioned this one in her talk, branch irreducible long of A up to height 10. So it says, show me all of the k-types up to height 10, and the long means it's some sort of nicely formatted output. So let's see. So ignore the S's. These are all constants 1. And this is a bunch of k-types, and they're labeled in terms of KGB element 0. And the first one is spherical, and the second one is 16-dimensional. So the coordinates are a little funny. Obviously, the 16-dimensional is the 2, 2, 2, 2 representation. So I kind of like to get some better coordinates for this. And it's possible to do that, and you do it as follows. You set BR is equal to branch irreducible A up to height 10. And then you say for mu in BR to fundamental weight coordinates of mu, I think, dimension of mu. No, unfortunately not. Huh? Oh, sorry. BR is a parameter. I need to get the monomials from it. For mu in monomials. Whoops.
No, for at mu.
Huh?
For at mu.
M?
At mu.
Oh, did that do it?
Yeah.
Of course, I knew that.
No. The representation is in
All right. Let me call it my cheat sheet now. Special A10. I have to load the file. No. All right, one more try. Highest weight, the lowest k-type. For mu, so I should say for at P, do for this lowest k-type of P, fundamental weight coordinates of the lowest k-type of P, and a dimension of lowest k-type type of P? I think this will work, maybe, I hope. Check. What was K type, oh, sorry.
Well, it can have is type.
Highest weight, I forgot highest weight, okay. So this case stuff is tricky, as you're seeing. So let's go slowly. I have this BR, and let's set NBR to be the monomials of BR. And let's set mu, or Q, is equal to NBR bracket 0. So what is Q? Q is a K-type. So tell me what to do on a grid. Highest weight? I can do highest weight, right? Fundamental weight coordinates of the highest weight of Q. Yeah, well, at least they didn't complain. Okay, so I can say for A in BR, do this fundamental weight coordinates of the highest weight of A. Put it in parentheses. One more. There we go. And then let's also tack on the dimension of the lowest K type of A? No. Lowest K type of A? There we go. Okay. So these are some decent coordinates now. The number again is the dimension. So this is the trivial representation of K. This is the representation, these are the highest weights on the 4 SU2 factors. And the thing with highest weight 1 is dimension 2. So this is dimension 16, 9, 9, 9, 9, and so on. Okay? Why are there repetitions?
Those 6 9s are
6 nines, yes.
uh,
6 nines, you're right. Yeah, they're all related by some, but it's the 1113s that bother me. Print, branch, irreducible, long of A10.
so what seems most confusing is that last parameter has a different lambda from the preceding 3, but it's giving the same highest weight.
Well, the preceding 3 don't have the same lambda either.
Oh, sorry.
They're very similar, probably related by the automorphism, but you're right. All right.
Here, all the weights are different, isn't it?
Hmm?
Here, all the weights are different, but in the other.
That's right. After I took the highest. So those. Well, no, but I mean, so I think I know what's happening. It's these 3 guys have the same lambda, but different x's. And I'm losing the x somewhere in my process. Yeah, so I know what's happening. It's that, in this list, I need to put in a KGB element somewhere. Set x is a KGB 0, And where do I want to put it? Highest weight A comma X maybe? No. Okay, let me not waste time trying to figure that out. All right, so let me tell you what the, all right, so first of all, Gordon asked about this representation, about its k-types, and that's what I'm showing here. Is it unitary? Gordon, yes. Let's do print.
Can you ask about B?
Yeah, print branch irreducible along B. So B has lowest k-type 16-dimensional. And I could convert these to the better coordinates, but I won't bother. That's what B is, and it's also unitary. These are two uniform representations associated to the orbit. 3311. How does that sound, Gordon? Is that the orbit?
Well, I kind of forgot.
I think it is. I think that's the orbit. And tomorrow, Jonathan, or maybe, I think tomorrow Jonathan's going to talk
Wednesday.
Wednesday. There's a whole side of this story that I'm not telling you about cells and unipotent representations and counting them and so on. I may come back and talk about that another day, but today I just wanted to focus on this one, just on k-types. Okay, so Gordon asked me a rather curious question. At least I thought it was curious. He said, take a k-type mu, and you can look at the dimension of mu upper h, where h is SU2 embedded diagonally inside SU2 to the fourth. Okay? And the conjecture was that every representation of spin 4-4 with infinitesimal character equal to lambda, gamma I guess I called it, a root, contains a k-type mu where the dimension of mu upper h is less than or equal to 1.
This was not conjecture. This was just my hope, because then a proof
Hope,
works.
okay. Hope.
I needed it.
Yeah, he needed this. This is a requirement.
I just prayed that to be true. That's all.
So, and the reason, and then if so, I forget the details. There exists. There is a space X, which is a representation of G, and you want to show X is equal to 0. Gordon had some lifting problem, and he thought he'd identified the lifting, and there was some part that he couldn't quite account for, and in order to rule it out, he discovered, that every k-type of X has dimension mu upper h greater than or equal to 2. Is that right?
Yeah, something like that.
I think that was
Yes,
it.
exactly. You can say that.
And Gordon can tell you why, exactly how this came about. I forget the details, but he therefore reduce showing x is equal to 0 to this bizarre statement? This is not the kind of question that we usually ask.
Although you should say that this SU2, which is really SL3, this is maximal compact in this SL3, right? So this principal series representation is...
This H
Yeah.
is really SO3, and it's equal to the maximal compact
This
of this SL3R.
That's right. So this is the general principal series have only types that have C that invariants. So it's not totally out of the blue.
Okay, so how on earth are you going to get your hands on this? Well, you have to do a little bit of thinking.
So
Yeah, got it.
the problem is that this representation, what you call B, right?
Say again?
Representation B, the minimal type, doesn't satisfy this. That was the problem for me. It's two-dimensional age invariance.
That's right. So let me say a word about that. So
Could you just pause and
Yeah.
calculate this mu upper h for this 2 tensor 2 tensor 2, just to,
just by hand.
yeah, just to remind us
Sure.
how that works.
So for example, suppose I took 1 tensor 1 tensor 1 tensor 1. That's the highest weights. So that's two-dimensional in each factor. What is the dimension of the SU2 diagonal fixed points in this? Well, the way you do it is you say that mu is 1, oh, excuse me, you break it up like this: 1 tensor 1 tensor 1 tensor 1, and 1 tensor 1 is equal to 2 direct sum 0. So this is 4-dimensional, and this is 3 plus 1-dimensional, and these are the highest weights. So it's 3-dimensional plus 1-dimensional, tensored with 2 direct sum 0. And so the answer, this is as representations of each of the SU, how do I say it? This is a representation of the first diagonal SU2, and this is a representation of the second diagonal to SU2. And so the final answer is this tensor product, which is 2 tensor 2, direct sum 2 tensor 0, direct sum 0 tensor 2, direct sum 0 tensor 0. And the multiplicity of the 0 representation is right here. It occurs once.
No.
No?
Two tensor.
The trivial. I'm looking for the trivial representation.
So that gives you one.
Oh, I'm sorry. There's also one from here. So that gives you one. And so this dimension is equal to 2. And so Gordon wanted to know that this representation cannot appear in space X, and this K-type doesn't tell you that. Lemma. Suppose you take A tensor B tensor C tensor 0 as a representation of SU2 to the fourth. Then the dimension of pi upper h is less than or equal to 1. And the proof is basically like this. The first thing gives you a plus b direct sum a plus b minus 2 direct sum dot 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 a minus b, assuming a is bigger than b, tensored with c. And how many times does the trivial representation occur in this tensor product? exactly once if C occurs between here and here and is the right parity, and 0 to otherwise. So that's a good exercise in representation theory of SL2. And so, question, does every P at this infinitesimal character in all have a K-type with 0? If so, you win. Okay? So, let's check. Now, I wrote, rather than wrote around, I wrote a little command to do this. It means it's trivial on one of those SU2s. All right, so let's set P is equal to all bracket 0 just to start. Or actually, let's take another one, 10. Lowest K type. Fundamental weight coordinates of this thing. Yeah, so this is what I want. These are the coordinates that I want. Dimension of the lowest K types of P bracket 0 is 4. So I'm just getting warmed up here. This is the right coordinates. I picked a random guy in the middle of the block to get it to work. So I have some parameter. I did add lowest K types plural because it might have more than one. I got the highest weighted lowest K type. That's got a bunch of zeros, but that's not the right coordinates. The right coordinates is the fundamental weight coordinates, where it looks like this. And just to confirm that those are the right coordinates, this is two-dimensional because 2 times 2 is equal to 4. So what I want to do is for P in all, do this thing. Okay, so I printed out the lowest K type of all of these 49 representations, or one of the lowest K types, in these coordinates. And many of them have some zeros. Here's the first one that doesn't. And that's probably B. Is that B? I think. Actually, so I should print the number. For P at I, do, whoops. What's wrong with that? Oh, sorry, I put the I in the wrong place. Okay, so there's the 49 representations with their numbers. And the first one, so all of these are ruled out from being in X by having a 0, except for some of them. For example, number 15. So we have to hope, so let's set P is equal to all bracket 15. Yeah, this is B. Print branch reducible long P10. So I'm not going to try and get the coordinates right, but we can see that the next K-type has dimension 27. And that's because in these coordinates, it's 2, 2, 2, 0. It's the only way you can get 27. So the completing the answer to Gordon's question meant for every one of the representations in this table where the lowest K-type doesn't have a 0, find another K-type that does have a 0. kind of a funny thing to do, but yes.
This 1, 1, 1, 3, that can also have one-dimensional, so you don't even have to bother with that. So.
No, 111 is 16 dimensional. 1 is the highest weight.
1, 1, 1, 3, I think that's
Sorry, what?
1, 1, 1, and then 3.
1113.
The representation 42, 43, 44.
You say those are okay?
Yeah, this will be one-dimensional at most. I mean, this is lemma is just one special.
Yeah.
So.
Okay, yeah.
They also permitted by triality, I guess, those three things, right?
I think that's right, yeah.
Maybe something like that, so anyway. There are not too many cases of this.
So anyway, at the end of the day, I was able to confirm Gordon's speculation. And I think it's a very nice exercise in learning how K-types work. Now, I'll just mention that there's a similar question about spin 5-3. And when I sent the answer to this question to Gordon about a year ago, he said, "Oh, that's great, thanks, really, that's wonderful. Can you also please check spin 5-3 for me at some point?" And then he made the mistake of saying, "No rush." So Annegret and I just got around to it the last couple of days, and modular checking on some details, it works also. But so I don't want to do that in detail, but I thought I'd just check the sort of numbers of representation.
How many?
Yeah, how many are there? So let's set, no, don't set G is equal to spin 5-3. And let's make all to be all parameters gamma for this G. It just occurred to me. Hi, I'm sorry. Be right back.
You gotta turn the microphone off.
David, you gave it away.
Sorry.
Yeah, so,
Okay, that's not so bad. And 11, my guess would be divided by 4, and so it's kind of similar.
gamma is the infinitesimal character, which in this case is a root.
Well, you fit all of the
Atlas never forgets unless it's told to.
So can you effectively this is,
Sorry, what?
so can you write down minimum K-types? I mean, the question is how do you choose coordinates? It's SP4 times SL2.
Yeah, the coordinates aren't so nice, but for P in all, do, let mu be the lowest K-types of P, bracket 0, in parentheses, mu, dimension of mu. That's one thing we can always do.
Yes.
So there are the dimensions of the lowest K-type. So the group is spin, K is spin 5 cross spin 3 modulo Z2. So presumably 3 is the 3 is the three-dimensional representation of this, and 5 is the five-dimensional of this, and 10 is
Symmetric squares, what's the dimension of symmetric?
sorry, what?
This is SP4. I mean, you know, so it has.
Yes, sim 5 is SP4 if you prefer.
So it has what, 4
It
dimensions?
has a 4-dimensional, yeah.
And symmetric square is what? 10 dimensional, right?
The thing was three-dimensional,
Oh.
sim five.
Ah,
It was trivial on the L.
yeah, there's S2. There's S2 of C5. I'm sorry, wedge 2.
No, but okay.
Anyway, we worked this out. It was a little painstaking because of the coordinates, but
So there are two representations with that minimal type, 10 dimensional.
yes.
So you see, actually, in this case, I also have two representations. One of them is spherical, right?
Yes.
The other has this minimal type, which is 10 dimensional, which is, then there are two ways you can get 10 dimensional, right? It can be 5 times
Yeah.
2 or 10 times 1001.
And
So
I'm
which
thinking
one?
it's,
It was 10 times 1.
was it? Okay.
Which one?
10 times 1.
10 times 1. Yeah, that's what I get, 10 times 1. But that's really that painful.
Was that one of the hard ones? I can't remember. Let me just wrap up. I just remember one other thing to do. Let's go back to G to spin 4, 4. We still have our L. We still have our TL. So just briefly, Gordon was also interested in inducing the 4 one-dimensional representations of L. Inducing from SL3R cross GL1 cross GL1, trivial tensor epsilon 1 tensor epsilon 2, the sign or the trivial on each of the GL1 factors. So how do you do that? So we have the trivial representation. What's the trivial representation on L? It's x equals 3, 1, 1, minus 1, minus 1, 1, 1, minus 1, minus 1, over 2, no, over 1 there. That's the trivial representation of L. How do I get a character on L? Well, I'm going to leave this alone. I'm going to add something to this, which is only going to matter mod 2, and is supposed to be orthogonal to the roots of L. So roots or co-roots? Co-roots of L, probably, right?
Orthogonal to the codes.
So I can add an integer to these terms. So I can take 1, 1, 0, 0, 1, 0, 0, 1, or 1, 1. Those are the 4 representations.